Hi, everyone. Today I'm going to talk about physics, artificial intelligence, and philosophy. Artificial intelligence, it's a data compressor, and when you compress data and it pops out with commonalities, that's part of what artificial intelligence, specifically neural networks, does. And so it looks like that it can find out those commonalities among things that seemingly unrelated, such as like the Fibonacci series. So I think it would be cool to create a AI thing that figures out common threads in the universe. So philosophy, the way it ties in with that is there's some kind of underlying, at least from my perspective, underlying thing that how is it that there's such common stuff among completely seemingly unrelated things, such as the Euler's identity, which is e to the I times pi plus 1 equals 0. And, e is the natural number, is found in nature a lot, and it's to do with, it's also found in finance. It's to do with continuous compound interest in finance, and it's to do with, I think it's like plant growth and stuff like that in nature, and as well as things like maybe bacterial growth and stuff like that. I is the imaginary number that comes out of certain, I believe it's engineering stuff. And pi is, it's used for stuff to do with circles and waves and a lot of that stuff. And 0 is, I've actually listened to a whole audiobook about 0. It's pretty cool. It's the number, it's neither positive nor negative, it's the in-between number. And the 0 used to not really be a well-known concept, and anyway, it is now, obviously. And so, and 1 is the number that everything, all integers are multiples of. So anyway, the e to the I times pi plus 1 equals 0 is a pretty cool thing. You can look it up if you want more details, or just let me know in the comments if you want to know more about it. So that's some cool things that I've noticed, and I'm going a little more depth right now. You can click off the video if you're bored, but but I'll just go into digging in more detail. So E equals mc squared. I was trying to understand from the fundamentals how AI is related to physics, because it looks like either physics or mathematics is the foundation of how the universe is created or how it exists. And from Khan Academy, that teaches a lot of mathematics and physics stuff, Salman Khan, he points out that he thinks that mathematics is the foundation, and on top of that is physics, followed by other things such as chemistry, and branching, built on top of chemistry is biology and geology and other ologies, like I should say. So the foundation is either math or physics, it looks like. And so I was digging down and trying to understand from the most fundamental details. And I started getting into trying to understand the big overview of string theory. Whether it's correct or not, don't know. It's mathematical consistency, but there's not any experimental direct proof of it that people know of at the moment. But it somewhat makes logical sense, it looks like. And it basically says that you can picture a string, and when you like thump that string and it vibrates certain ways, that becomes a subatomic particle like an electron. If you thump it and it vibrates a different way, that could be like an up quark or down quark. And protons and neutrons inside of atoms are made of up and down quarks. So the strings in string theory are what make up those elementary particles. And supposedly their length is approximately 10 to the negative 35 meters. And that's approximately the Planck length, if I understood it right, which is the minimal length that can exist in the physical known universe. And that's some other pretty cool things. So the energy is, if I understood it right, something to do with the energies of those vibrating strings some way tie in with Einstein's E equals mc squared. And you can use stuff to do with dot products to calculate things with E equals mc squared. And dot products is most of the calculations that artificial intelligence does, or a big chunk of them. And it's pretty neat to me how you can see sort of threads all the way from the most fundamental, at least a hypothesis that people know of, up through how artificial intelligence works. And that's pretty cool from my understanding. And other things, I'm trying to think of some more examples. Oh, also a sphere like the sun or basketball or the earth. You can calculate the volume of it specifically with 4/3 times pi r cubed. And with a basketball, just say if you calculate in inches, the radius, the r, just say however many inches the radius of basketball is, just say like 8 inches. So you'd cube that. So 8 to 8, 64, and then 64 times 8, whatever that is, you'd multiply that by 4, divide it by 3, so that's 4/3 times pi r cubed, and that gives you the volume of the basketball. But you can do the same exact thing for the earth. It'll give you the volume of the earth in cubic inches as well. Or the sun, it'll give you the volume of the sun in cubic inches. I actually built a computer program, just small number of lines of code, like 2, 3, 4, 5 lines, that calculates that. Put in the radius, and it comes up with the volume in cubic inches or cubic units. So that's a pretty neat thing, and it's such a simple formula, relatively speaking, and it'll work for basketball, the whole earth, or the sun. And the sun's size is, you can fit 1 million earths in the sun. I don't know if it goes by volume or by mass, but basketball, the earth, or the sun, or other planets. And also another common thread is gravity. So gravity, as long as you don't get into high speeds and stuff like that with Einstein's relativity, Newtonian version of gravity is F of g equals m1 times m2 times big G divided by r squared. And F of g is in newtons, and the m1 and m2, each of those are the masses of the objects that are gravitationally attracted in kilograms specifically. And then big G is something like 6.67 times 10 to the negative 11, some units, whatever. And then divided by r squared. The r is in meters, and so you square that. So what it's saying is there's a constant, which is the gravitational constant, the big G, and it's multiplied by the masses or the product of the masses of the two objects that you're calculating the gravitational attraction with, divided by the distance in meters from the centers of masses of those two objects. And that, as far as people are aware, works on the Earth, the Sun, Jupiter, Neptune, Saturn, Pluto, etc. And as far as people are aware, it works in Alpha Centauri, which is the closest star system, with Alpha Centauri A and B, closest star system to the Earth, the closest stars to the Earth besides the Sun. And it works in the Milky Way galaxy. I guess people have measured it in the Milky Way, and the Sombrero galaxy, which is way over 100,000 light years away, probably, because the diameter of the Milky Way galaxy is about 100,000 light years. So that m1 times m2 times big G divided by r squared works in all those things like a thread that's among all of those. And that seems pretty neat to me. It's like there's underlying threads that are woven throughout different places in the universe and throughout different subjects as well. And like the natural number E that was mentioned earlier, it's used inside continuous compound interest and stuff to do with plant growth and stuff like that. And it's used in finance, or it's used in finance with the continuous compound interest. And so that seems kind of cool as well. But it's also used in artificial intelligence. When you create a softmax function for classification, what happens is it outputs things called logits, which are the log probabilities. I don't forget what it stands for, but it outputs basically raw numbers that could be like negative 2.04, positive 3.197, whatever. So those, if you take the formula for the softmax is e to the x divided by the sum of all the e to the x's. So you have e, which is that number found in nature and compound interest and so on, raised to the value on the top of the fraction, raised to the value of one of those logits and one of those outputs of the neural network for its prediction. Just say for predicting if a picture is a 0 through 9, like the MNIST data set, 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And there would be 10 logits or 10 outputs from that neural net. But you wanted to convert it into a probability distribution that if you sum all the probabilities, it totals 1. So what you can do is, one way to do it is to take e raised to, just say that whatever output from the logits for the value 0 is, say e raised to that power, and put that on the top of the fraction. Then on the bottom of the fraction, you say e raised to that power plus e raised to the power of whatever output of the logits for the number 1, and plus e raised to the power of whatever the output of the logits for number 2, and so on up through 9. And so that gives you the probability sort of that 0 in relation to the total. And then you go through the thing again, like put it in a loop or something, and then do that for 1 at the top of the fraction divided by the sum of all of it. And you know, the e to the x divided by the sum of all the e to the x's, and keep doing that for all 10 digits. And that'll give you a probability distribution. And then you can feed that into the log loss, which is also called categorical cross entropy. But more specifically, you can take a one-hot encoded vector, which is basically a list of zeros, except there's a 1 in a specific location, and that's for the target class. The target class is the specific one that it should be. Like when you're teaching the neural network, you pass in a picture of a 1, for example. The logit, or the output, from the softmax, the probability of the output from the 1 section, you can multiply all the others by 0 except that one. So whatever the probability is, just say it's 0.3, that the answer is 1, that it predicted. So then you would take that 0.3 and put it into the negative natural log. So you put that into the natural log, and then you take the negative of that, and that will give you the loss for that. Then you can back propagate through the neural network, calculating the local derivatives for each thing with respect to the previous thing, or each local derivative. Then you chain all those derivatives together by multiplying them, unless it's certain things to do with adding. If it's certain other stuff, then you add the answers together, and that will give you what the weights that will give you the amount that, if you barely bump up the weights, barely increase one of the weights, then how many times that increase does the loss change? Like if you bump it up by 0.01, and then the loss changes by a tiny bit, you can take that change, like you take the current loss divided by the current loss minus the previous loss, and divide that by the 0.01 or whatever I said earlier. And that will tell you the numerical derivative for that. But in practice, you'd use the whatever you call it, the actual derivative. And so, like you have f of x plus h minus f of x divided by h, which is just sort of a different version of the y2 minus y1 over x2 minus x1. So the x2 minus x1 in that case is, x2 is the original x plus a change in the x. So you have x, and then if you have the answer over here for the next point, that's whatever x is plus a change in it. So you have x, and then you have plus h, you have x, and then you have x plus h. So you have the x plus h minus x, and so that just gives you h, and that's why h is on the bottom of the first principles formula for derivative. So you have f of x plus h minus f of x divided by h, and that will tell you if I barely bump up one of the weights, how many times that bump up does the loss change. And so once you have that answer for each of the weights and biases, if you use those, and that will give you stuff that you can work with to update the weights so that it decreases the loss, and the neural network guesses closer and closer to the correct things. And it can then find patterns among those specific things. And like, what is it that makes the picture of a 0 different than a picture of a 1 or a 2 or a 3? And that way it can learn those common threads and patterns. And that seems to be what neural networks are really good at. So hopefully they can figure out commonalities in the physical universe and help people to come up with useful inventions and so on. So anyway, I guess I'll stop the video here. If you have any questions or comments, let me know. Thanks for listening, and be sure and hit like and subscribe so that I'll know people want to watch more of these. And thanks, and wish you the best.